Okay, this question right here, it is very intimidating at a first glance. It does look impossible, or at least very difficult if you haven't solved anything like it before. But at this point, and this is true for every Calculus 2 class, you are starting to see so many techniques, and the questions, they're all rigged in a certain sense so that at least one of the techniques or several of the techniques put together work to make the question or the integral feasible, solvable. So how do we make this one especially solvable? The first issue that I see in here is that I have sine of x, and then I have the cosine of 2x, and that's a problem. I have two different angles involved. One is x, the other is 2x. So I want to make this situation go away. I want to make a simplification of this so that both instances or all instances of angles, trig functions, they are referring to the same angle. So I want it to be sine of x, cosine of x. If a tangent shows up, I want that tangent to also be the tangent of x. So all trig functions need to be functions of the same angle. That's my first move on this one. And what I will use is the double angle formula for cosine. So the cosine of 2x is the cosine squared x minus the sine squared x. I pay a price for this. I have the angle, but the price that I pay is that I increase the power of cosine, and a sine squared also shows up. So it is the price of doing business. I think it's going to pay off still, so let's keep going. I have the sine x times the cosine squared x minus the sine squared x. So that is, this. Maybe I can do it in blue. And then e to the cosine of x dx. I'll handle this e in a second, but right now, as I look at it, you can see, together with the e to the cosine, I have another cosine squared, but I have a sine x that can easily be absorbed together with this dx. So if I could change this cosine into a u using a u substitution, right? I could make du depend on sine x dx. So that would be my du on the outside. So as long as I can change this expression here in things that only depend on cosine, which is my u, I'm golden. So that's what I'll try to do. My next change is to make sine squared x as 1 minus cosine squared x. So I'm going to make this change. So I have my sine, and just to be practical, I'm going to put this sine right over there. So sine x dx. And then I'll keep the e to the cosine x right here. And now I'll handle this blue part, which will be cosine squared x minus, and remember that the sine squared is 1 minus cosine squared. That's 1 minus cosine squared. And then I can write this as 2 cosine squared x minus 1 e to the cosine x sine x dx. It may look, to somebody inexperienced with calculus, it may look that I've done nothing, that things are just as bad or sometimes even worse than what they were when we started, but in fact, this is so much better because of the strategy we just talked about. If we make u equal to the cosine of x, making a substitution, using the substitution rule, or u substitution rule, du is minus sine x dx. The derivative of cosine is minus sine. This expression now, right, you have this in here, and this expression turns into a 2u squared minus 1 e to the u du with an extra minus sign from here. Okay, so this is a lot better already. Maybe not a lot, but significantly better. You can already see that you had 3 terms multiplied together, and now you only have 2. So it's already an improvement. Moreover, now looking at this, I'll let you absorb the idea. Maybe I want to do somehow handle this minus sign on the outside, maybe not. But if you notice, you have now these 2 terms that are multiplying. This one, if you derive it enough times, this is a polynomial function in terms of u. If you derive it once, you get 4u. If you derive it again, you get 4. If you derive it again, you get 0. So that's going to disappear eventually after enough derivations. So this here you can integrate pretty easily though. The integral of e to the u is e to the u. If you integrate, it's e to the u. You can integrate infinitely many times without any extra complication arising. So when this derived becomes simpler and this integrated does not become worse, we may use integration by parts, okay? And because how many times it took for this to disappear? 4u, and then 4, and then 0. So it took 1, 2, and then the third derivative here. That means I need 2 integration by parts done for this to work. So this is a problem that I could solve with 2 integration by parts. 2 integrations by parts. Instead of doing that, you may do that if you are okay, if you're fine with that. And you should be okay with that. But a much faster way is to use the tabular method. So we're going to use the tabular method for integration by parts on this. What I will do, like I said, first is I will distribute this minus sign to just this. I don't multiply to the whole thing. When I multiply something by a product of 2 things, I multiply by one of the 2 things, not by both. So I multiply this by minus, so I get minus 2u squared plus 1, just so I don't have an extra minus sign on the outside to care for. And then what I will do is, okay, the thing that derived becomes simpler will be my u, so that is 1 minus 2. Maybe I'll use a different color. And maybe what I'll do here as well is to not call this u, because I'm already using a u here, so I'm just going to derive this as many times as I need for it to go away. And then I'll keep the e to the u here on this side. So this I derive as many times as I need for it to go away. So I derive it once, I get minus 4u. Derive it again, minus 4. Derive it again, 0. This one I integrate just as many times. So integral of e to the u is e to the u. Integral of e to the u is e to the u. Integral of e to the u is e to the u. Okay. And now I multiply them crossed like this. This is the tabular method to simplify the result of the integration by parts. And you gotta be aware of the sign change. So be careful so you don't mess this up. And I'm gonna look it up on my notes just so I don't figure it out. So just so I don't mess it up. I think it starts with a plus and then goes minus. So plus, minus, plus, minus. Yeah, that's correct. But just wanted to make sure. So it's plus, minus, plus, minus. So the answer then will be this product here with a minus sign. So minus 1, and maybe I'll put it below here just so it all fits. Minus 2, excuse me, minus 2u squared e to the u. So this is the first term with the minus sign in here. And now the next term is this one with a plus sign. There's already a minus here, so I don't change anything. So minus 4u e to the u. It's this term. And then with a minus sign, right? So this is going to turn into a plus. This is the last term, plus 4e to the u plus c. And you can already see, if you're familiar, if you've done enough integration by parts practice, you can see that this has sort of the hallmark format of an integration by parts, several integration by parts problem. You have something with powers that decrease, you know. So this is power 2, this is power 1, this is power 0, degree 0, right? And something that repeats or is periodically repeats. Right? So this is the hallmark type of problem for integration by parts. I'm going to do the thing I did with the minus again, because I don't want to have to handle this minus separately. And now I have to be careful with the fact that I gave myself, I used the u substitution to be able to do this. So before I write the final answer, I have to change back from variable u to variable x. So remember what u was. U was the cosine of x. So that means this is 2 cosine squared x minus 1 e to the cosine x minus 4. And u was the cosine of x. E to the cosine of x plus 4e to the cosine of x plus c. So that looks very wild, very weird, but it is a function that I could evaluate if I want. I can plug in some x value, x equals 0, x equals pi or something if I need. So it is the result of the integral. We had to use several techniques here. The trick, the key idea to understand it and to solve similar problems is to see what are the triggers, what are the characteristics of the expression that will lead you to make a certain decision and use a certain tactic. So, initially, the first trigger I pointed out was sines and cosines of different angles. Sine of x, cosine of 2x. Those are different, which makes it difficult for me to combine them somehow. So first thing, get rid of the 2x, turn into an x using a double angle formula. That was a double angle formula. The second strategy that we mentioned after we've done this was noticing that I had e to the cosine, and that would be something very difficult to solve unless I made a u substitution, e to the u, right? U equal to cosine of x. So I planned for this step earlier, and then I noticed that there was a sign in here making that step possible. So I needed the rest of the expression to depend only on cosine. So change that sine squared into 1 minus cosine squared. And then that turns out to be this. I make the u substitution I was looking for. And getting this, I can see now the final trigger, the final characteristic of the expression that makes me make a decision of a strategy. I know that it's two things multiplying. If I derive one of them enough times, it becomes 0. And integrating this one is fairly easy. It doesn't get it doesn't get more complicated. So this is how you solve this type of problem when you need to use several strategies. Just make sure you know what characteristics should prompt you to make a decision or another.